Hi folks, welcome to the Math 611B Concept Roundup for sections 3.1 to 3.3. This is just an idea of the topics that we covered during those sections. If you're using this to teach yourself the material the first time, I'm not sure how well it's going to work. I strongly recommend as we go through this and we hit an example that you press pause and you work through the example yourself and then double check with my solution rather than just watching it be done like some sort of performance piece. Okay, here we go. So derivative functions, that's what we took a look at first in 3.1. And in the last chapter, we looked at slopes of tangents at specific points. Derivative functions give the slope of the original function at any point. Okay? And there are common notations. So you might see y prime or f prime or dy by dx, or d by dx of f of x. They all mean the same thing. Okay? They mean the slope function or the derivative function. The derivative is found using this first principles formula. And it all just stems from our basic slope formula, using points that are infinitely close together. So it's the limit as h goes to 0 of f of x plus h minus f of x all over h. If we've got that and we want to find f prime for this specific function in example 1 by first principles, then we've got to know a couple of things. We've got to know, first of all, what f of x is. That's no problem. And we need to know what f of x plus h is in order to be able to sub it in to this. Okay, so f of x plus h is going to be 3x plus h all squared plus x plus h. I just put an x plus h in wherever I had x in the original function. Okay, work this out, expand this binomial. Plus x plus h. That's going to give us 3x squared plus 6xh plus 3h squared plus x plus h. There's the function at x plus h. Okay, now we'll use the definition of a derivative. And here it was. So this is where we start from anytime we want to use first principles. We did all the work in advance. We figured out what f of x plus h was. So it's this long thing here. 3x squared plus 6xh plus 3h squared plus x plus h. And this is all over h. And I also need to subtract off f of x. And make sure I put it in brackets. Okay, I'll keep going with that. So notice up top, the 3x squared and the 3x squared, those are going to be gone. The x and the x, those are going to be gone because we're subtracting them off. So we're left with 6xh plus 3h squared plus h all over h. If we divide everything by h, then we get 6xh plus 3h plus 1. Okay, so what happened here is those divided out. Left us with 1. And as h goes to 0, what we're left with is 6x plus 1. That's what f prime of x is. Okay, great. So we've got this expression. Remember what it tells us. So the original function was 3x squared plus x. This new one down here, the derivative, tells us the slope at any point. So if I put in a 1 into this function down here, that would tell me what the slope of the tangent is where x is 1 on that original curve. And the original curve was a parabola. We know that. Okay? So when we see f prime or dy by dx, we're thinking slope function. You might be asked to graph f prime from the graph of f of x. And so, again, f prime, rather, gives us the slope of f of x at every point. So we're trying to make a graph that tells us about the slope of the original. Here are the things to look for in a graph. Look for horizontal tangents. Okay? That means, if you've got a horizontal tangent, that means it's a slope of 0. Or on the f prime graph, there'll be x-intercepts. They'll have a value of 0. So let's go down below to this graph. It looks like this. Let's try and find some horizontal tangents. So positive tangent, positive tangent, positive tangent, positive, positive, getting smaller. Right here, we'd have a horizontal tangent, which means a slope of 0. On the derivative function, you'd show that slope being 0. So it would be that red point. Okay, keep going. Negative slope, negative slope, negative slope, negative slope, negative slope. Ah, horizontal tangent again. So that means a slope of 0, or the derivative has a value of 0, x-intercept on the derivative. Okay, if I go, say, over here, that is a very steep positive slope. So I'm going to show that. Steep positive slope means a big positive number for that slope. I don't really know how big. I'm just sort of estimating the values, but I'm going to get the shape properly, whether I have the actual values or not. Okay. The most important point, other than the x-intercepts, are where the curve is at its steepest. So if I go through here, it's super duper steep, super steep, super steep, super less steep, less steep, less steep, 0. And then I go on this little negative slope part. Right here, that is where the curve is at its steepest, over that little interval. And it's a negative slope. So that's going to be as far down as the slope goes on that little interval. And you might want to grab just a few others. So if I go back here on the left of the curve, oh, that's really steep and it's positive. So that's going to be a huge positive value. Okay. And I start to connect these together. And I'm going to get roughly this shape. It's not perfectly drawn. It should look more or less like a parabola on this one. But the important points were, right here, horizontal tangent. Right here, horizontal tangent. And this was the steepest, so it became a minimum. Okay? So you can do that with various shapes of curves. The next thing we talked about was in 3.2, differentiability. So differentiability means, can you find the slope of the function? If we can find the slope of the tangent at a point on a given function, we say that the function is differentiable at that point. And differentiation is just the process of taking the derivative. So if it's differentiable, you can find the derivative or the slope at that point. With the exception of endpoints of functions, in order for a function to be differentiable, it must tend toward the same slope as we approach from the left or the right. And the reason we have an exception with the endpoints of functions is because you can't approach an endpoint from both sides. So that seems like an unreasonable expectation. There are 4 cases where functions are not differentiable at a point. The first one is a corner. So if we have y equals absolute value of x, that function looks like this. Almost everywhere on that function, you can find its slope. But the problem place is right here. From the left, the slope is -1. From the right, the slope is 1. They're not converging on anything. There's not any kind of soft landing towards that slope. It's just a corner. So what we would say is, this is not differentiable, but only at one value. It's not differentiable at x equals 0 because of the corner. It's differentiable everywhere else. Okay? But that's a problem spot for finding the slope at x equals 0 on that curve. A cusp is the same sort of thing, but involves curves. So if I had something like this, square root of the absolute value of x, that happens to look like this. And you could take your smartphone and get it to graph it, and you'd see it looks something like this. Notice as we approach from the left, the slope would be negative infinity. As we approach from the right, the slope looks like it's going to be super steep and positive. They're not converging on the same value. Okay, so that means not differentiable at x equals 0. So anytime you see a cusp, it's not differentiable at that point. Vertical tangent. So we might see a curve that looks like this. Cube root of x. We saw that last semester. It looks something like this. Right here at x equals 0, this curve goes momentarily vertical. And there is no number that represents the slope of a vertical line. Its slope is undefined because it has infinite rise and it has no run at all. So it causes you to divide by 0. Whenever you see one of these vertical tangents, once again, not differentiable at those points. Okay, and lastly, anywhere there's a discontinuity, it's not differentiable. If the graph doesn't exist, it's pretty hard to talk about its slope. And even if it does exist, but has, say, a jump or an infinite discontinuity, then we've got trouble. Its slope is not going to be the same from both sides. Okay, so we might have something that looks like, I don't know, I'm just making something up here. That, and does this, and I don't know, make that a solid dot. Okay. This is not differentiable at -2 because of the jump discontinuity. It doesn't go to the same slope from both sides. At x equals -2. Okay. It's not differentiable at x equals -1. There's a removable discontinuity there. And it wouldn't matter whether that was just a hole or whether it was a hole with another value up here. It would still not be differentiable at that point. It's also not differentiable at x equals 1 because there's an infinite discontinuity there. Okay. So if you have a discontinuity, not differentiable at those points. Let's take a look at a little function here. Okay, so we want to figure out where this one is not differentiable. If I trace along it from the left, no problem, no problem, no problem, no problem. Right here at x equals -2, no good, because there's a corner. Okay. And then this whole section is fine until we hit right here. X equals -1. You've got another corner there. Keep going. X equals 0. You've got a discontinuity. And it doesn't matter what kind of discontinuity. It's not differentiable at a discontinuity. And then at x equals 2, it's not differentiable. Okay, remember the first thing we looked at was finding the derivative function, and it was somewhat painful because we had to figure out f of x and f of x plus h. Section 3.3 is all about finding little rules excuse me, and shortcuts that spare us from having to use first principles and allow us to find derivatives quickly. We proved all of these in class, and that's why we can use them. So the table on the right is just saying if you have a constant, its derivative is 0. So this says y, this is dy by dx. If you have x, its derivative is 1. X to the n is nx to the n minus 1. So the power goes down by 1. The old power comes down front. The next one right here, this is saying if you have constant times a function, then your derivative is going to be constant times the derivative of that function, which is just as you would expect. The next one, the sum and difference. So the sum of two functions, their derivative is just the sum or difference of their derivatives. So that's exactly as you would expect. There's not a whole lot of surprises here in the first 5. Then we have the product rule, which says if you've got u times v, where u and v are both functions of x, then it's going to differentiate in terms of u prime v plus u v prime. Same thing for a quotient. And again, we proved these in class. If you have u over v, then it's going to look like this. Okay, let's put these to use. So we want to find dy by dx if y is 3x squared plus x. So the constant multiple rule would say, I can still call this 3. The x squared is going to turn into 2. The 2 comes down front. And the power goes down by 1. So it's 2x to the 1. Plus x, the derivative of x is 1. Or 6x plus 1. And a lot of people would just jump to that. 6x plus 1, they'd be thinking 3 times 2 over here makes 6. Power goes down, so 6x. Okay, think about how much faster that was compared to the first time we did it, which was over here. This is the exact same question as example 1. And it took us a lot of work. And oh my gosh, we got the exact same result. So the derivative rules, the differentiation rules are nice. B, we've got 3x to the 4th minus 7x squared plus 2x minus 3 dy by dx. So this 4 is going to come down and get times by 3. So we'll get 12. And the power goes down by 1, so 12x cubed. Next one, 7 times 2 makes 14. And the power goes down by 1, so you've got a regular x. Next one is going to be 2 times the derivative of x, which is just 1. And this minus 3 here, its derivative is 0, because it's a constant. Sometimes we get a little messed up with the radicals. Think of them in exponential terms. So root x is x to the half. That means dy by dx means your power comes down front, and your power itself goes down by 1. So it was a half. A half minus 1 is negative a half. Or you can write this, if you prefer, as 1 over 2 root x. But you would do that after having put it in exponential form. Okay, D and E. These are product and quotient rule questions. So in D, you could just FOIL it out and then differentiate regularly. Let's get the practice in, though, for using the product rule. So here we have two things that are multiplied together, and they both have x's in them. That's when we use the product rule. So I'd say that the first thing that's being multiplied, that's my u. And I'd also like to figure out what u prime is. So if u is 3x plus 1, u prime is 3, using our little differentiation rules. The next thing that we're multiplying by, that's what we call our v. And its derivative is 4x. Okay, dy by dx, from right up here, is u prime v plus u v prime. Okay, or 3 by 2x squared plus 5 plus 3x plus 1 by 4x. Work it through. That gives us 6x squared plus 15 plus 12x squared plus 4x. Or 18x squared plus 4x plus 15. And if you had FOILed it out first, you would have got the exact same result. So that's what the derivative function is, or the slope function. E, same sort of idea, but this time, obviously, it's a quotient. So I would say U is whatever's on top. Its derivative here would be 6x. V is whatever's on bottom. Its derivative is 2. And now we're going to work it through with the quotient rule. U prime V minus UV prime all over V squared. Okay, so that makes for 6x by 2x minus 1 minus 3x squared plus 1 by 2 all over 2x minus 1 all squared. Okay, gives us 12x squared minus 6x. This will be minus 6x squared minus 2. Six x squared minus 6x minus 2 all over 2x minus 1 squared. And if you like, you can factor the top. It's a good habit to get into, just in case there's anything that divides out. In this case, though, there isn't anything that divides out, so it doesn't get us a whole lot further ahead. So I'd accept either one. Okay. But those are two equivalent expressions for dy by dx, and all we did was follow the quotient rule. Knowing these rules makes it easier and faster to find equations of normals and tangents. So if we want to find the equation of the normal to y equals 2x squared minus 3x plus 1 at x equals 0, we need to know a point, okay, and that point has an x value of 0. And if I sub 0 into this, I'm going to get a y value of 1. The other thing I need to find for an equation of a line is the slope. And that's what derivatives are good for. They give you the slope of the original function at any point. Okay, so let's find out what dy by dx is. We had 2x squared minus 3x plus 1. Its derivative, therefore, is going to be 4x minus 3. We want to find out what's going on at x equals 0. dy by dx would be 4 times 0 minus 3, or just negative 3. Great. What does that mean? It means that when x is 0, the slope of the tangent is negative 3 on that original curve. And if we take that one step further, since this is asking about the normal, the slope of the normal would be the negative reciprocal. So negative negative makes a positive. Flip this over and we get 1/3. Now we have everything we need to find the equation of a line. So the equation of the normal will look like this. Y minus y1 equals mx minus x1. Point slope formula. Okay. For us, we had a slope of 1/3 and a point from up top of 0, 1. So I'll have y minus 1 equals 1/3 x minus 0. Work it out, get y on its own, and we'd have 1/3 x plus 1. And if you graph that on your device, then you'd see the original with the normal rather. You'd see that this really does look like a normal at x equals 0 on that original curve. We're going to revisit differentiability just briefly here, because we might have a piecewise function that we want to figure out if it's differentiable kind of at its split point. The easiest thing to do with these is to sketch them to see if it's even remotely possible. So if you sketch it and you find a discontinuity, or you find something that's obviously a corner, then we can just say no. So sketching this function, I know what x squared looks like. Looks like this. Okay, and I'm talking about what's happening at 2. So this only looks like x squared up until x is 2. And if I put a 2 in for x, I'll be at a y value of 4. Now let's do the next part of the function. 3x minus 2 for x is greater than 2. So if it doesn't meet up with that parabola, then we're sunk. There's obviously a discontinuity. So let's put 2 in here. That would give us 6 minus 2. Oh, it really does happen at 4. And it's got a fairly steep positive slope, so I really don't know. I can't discount that it's differentiable. It may be differentiable. It looks pretty good, actually. Doesn't look, well, maybe it's a corner. We'll need some algebra to investigate. Okay, and to do that, we have to figure out if it's coming to the same slope from the left and the right. So from the left, it has this definition. F of x is x squared, meaning that f prime is going to be 2x. And at x equals 2, we'd have f prime of 2 would be 2 times 2, or 4. So from the left, we're approaching a slope of 4. Let's see what's going on from the right. From the right, the function's defined by 3x minus 2. That has a derivative of 3. And at x equals 2, since there are no x's in there at all, it's still going to be a 3. Ooh, that says that the tangent from the right is 3. Since those are not equal, it's not differentiable at that point. If they had turned out to both be 4 or both be 3, then it would be differentiable, and it would look smooth right at x equals 2. Here, we've got a little bit of a corner. So, since the function doesn't approach the same slope from left and right, of x equals 2, it is not differentiable at x equals 2. And you could have done this with first principles instead of using our differentiation rules, but it's a little bit easier this way. Excuse me. Okay, one last thing we're going to take a look at, which is higher order derivatives. So the derivative of the derivative is called the second derivative. Shocker. There are common notations for it. So you might see y prime again, so y double prime, or f double prime, or looks like d squared y over d x squared. Those are common notations for the second derivative. So if we want to find the first derivative, first 3 derivatives of this, well, the first derivative's no problem. 5 times 4 makes 20. Power goes down by 1. 3 times 3 makes 9. Power goes down by 1. 2 times derivative of x is 1. Y double prime just means find the derivative of y prime. So 20 times 3 makes 60. Power goes down by 1. 9 times 2 makes 18. Power goes down by 1. And 2 was a constant, so its derivative is 0. Y triple prime, that's the third derivative. It's going to be 60 times 2, that's 120. X minus 18. So those are all the concepts that we've covered up to March break in Chapter 3. I hope you found this at least somewhat helpful, and I'll see you in class.